And so we don't have a whole lot of time left, but there were a couple things that I just thought would be good to discuss before we end. So you were very clear, and you have been just now again, that this is all in the context of a particular approach to trying to put gravity and quantum mechanics together.
Yeah.
What hope do you see for then taking these ideas over to quantum gravitational theory that would be closer to the world as you know it, positive cosmological constant, things of that sort?
Yeah, so I mean, I'm working on that now, right? So that's where I want to go, right? I mean, quantum cosmology is sort of the most confusing subject in science, I would say, in some sense, because you're trying to talk about the universe as a whole, um, and you, the observer, are a small part of the universe. And in particular, if you believe that something like string theory is true, then in sort of a realistic cosmological setting with a positive cosmological constant, then as you know, the different solutions of string theory all sort of get mixed together dynamically, and it seems hard to have a theory of the whole thing without just having the whole theory of quantum gravity. Um, that said, one of the things we have learned from black holes over the last 10 years is that these low energy effective methods, like the quantum extremal surface formula and the gravitational path integral, are surprisingly knowledgeable about what's going on in the fundamental description. And so, a natural thing which we can try to do is apply those methods to more realistic spacetimes like de Sitter space, um, and see what they tell us. And in particular, there's some seemingly totally crazy thing that they're currently telling us, which I and others are trying to understand, which is that if you have quantum gravity in a closed universe, with no spatial boundary, then the number of fundamental degrees of freedom is zero, which sounds totally nuts, right? And yet, if you believe everything that we were just saying, the holographic principle and so on, right? Well, the holographic principle says all the fundamental degrees of freedom are out at the spatial boundary. And so if there's no spatial boundary, then what
Well, I always
fundamental?
thought it would be like the cosmological horizon intuitively for de Sitter space, but you're telling me that's not the right way of thinking about it then.
Yeah, so that's one of the ways that you try to think about it. But if you try to think about it on global slices, where you think about what's happening in the whole universe,
Yeah, sure.
uh, which, in the black hole context, before people said, oh, well, you probably shouldn't think about it on global slices. Oh, nobody can really go in and look all the way at the shell that made the black hole. We're outside. We should just think about it from the outside. And people often said that similarly in de Sitter, you should just think in the static patch
Yeah.
within one cosmological horizon. But one of the things we learned is that the global picture is sometimes correct. Like to do this quantum extremal surface calculation of the entropy of the Hawking radiation, you need to use the global picture. It doesn't work unless you use the global picture. And so there's at least some sense in which that picture is meaningful. Um, and it's kind of our job to understand, to what extent is it meaningful? Um, but then, yeah, I mean, and you immediately run into this problem of 0 degrees of freedom to describe the whole universe, which it sounds totally nuts, right? Like, how can
So
there be?
what do you do with that?
Well, yeah, so I just wrote a paper about it. This is one of my more crazy papers, so I'll say it because I'll tell you a little because I know you like this kind of thing. Um, so the idea that we proposed in the paper is that you have to explicitly include the observer who is measuring things as part of the discussion of the system. Because if you're in a closed universe, there's nobody outside the universe. And so we interpreted the 0 degrees of freedom as saying that nobody can measure a closed universe from the outside. You can only measure it from the inside. And so we proposed a way of doing calculations in the one-dimensional Hilbert space based on this picture of the code where you have an encoding map from an effective to a fundamental Hilbert space, here with the fundamental Hilbert space being one-dimensional. Um, but that somehow we came up with a set of rules where if you restrict to states which have an observer, and you impose a rule, which kind of gets back to what something you said at the very beginning of the conversation, which is that in order to be an observer, you have to be classical. And so we sort of promote that to a principle of nature, that in order to be an observer, you have to be classical. Uh, and then we found a way of doing calculations in a one-dimensional closed universe with an observer who is present that agree with the effective field theory calculations up to errors which are suppressed like e to the minus the entropy of the observer. And so, if you're a big observer with a, big brain
Usually
and a lot of
suppressed.
memory, and
Yeah.
you can match effective field theory to a pretty good
Right.
approximation, but it's not an approximation that gets arbitrarily good when you take Newton's constant to zero, because because they're still just irrecoverable errors that are left over from the fact that your brain has finite size. And this gets at something which I've thought for a long time, which I think quantum mechanics itself has to be emergent. And what's the limit in which quantum mechanics is emergent? It's the limit where the observer is infinitely big. Um, and you can get away with that without gravity because you can just make them really heavy and it's fine. But when you have gravity and you try to make them really heavy, they can collapse into a black hole. And so to avoid that, they can't be so heavy. And now we need some generalization of quantum mechanics to finite size observers. Um, and so we proposed some formalism for this in this somewhat crazy paper that we just wrote. And so, I should be clear that this is not something that I've, convinced the whole community of. I'm not totally sure I convinced myself of it either. Um, but it's
Right.
sort of the level, it's an illustration of how far you have to go
Yeah.
to
Yeah.
try to
Yeah.
get
Yeah.
at these hard problems of holography and quantum
I mean,
cosmology.
Tuft, of course, has been thinking about a theory that would underlie quantum mechanics and quantum mechanics would emerge from it. Does your work have any relation to things that he has
Yeah, I
been
think it's
talking about?
different because he wants things to be secretly classical. And I don't need that. Yeah, he wants to have some classical theory with a lot of degrees of freedom that somehow fakes quantum mechanics with a lot
Uh-huh.
of degrees of freedom. I'm okay with the world being quantum mechanical. That's okay. But what I want is what I call emergent quantum mechanics in the sense that there's some parameter where as I take it to infinity, I recover the usual sort of Copenhagen quantum mechanics. But then now with this parameter, if I take it to zero, then I get this one-dimensional Hilbert space. And so
Right.
I can sort of interpolate between the Copenhagen when the observer entropy is infinity and a one-dimensional Hilbert space when the
Right.
observer entropy is zero. Um, but I think to motivate this, you really need gravity. I don't think it can be motivated just by sitting
Yeah.
around
Yeah.
and
Yeah.
saying, "Oh, I
Totally
think quantum
understand.
mechanics is weird." I mean, in fact, I don't think quantum mechanics is that weird, to be honest. I think it's the weirdness is exaggerated.
Yeah.
Um,
I don't know. I think it's because you're younger.
I mean, I go through
I think
phases,
it's pretty
but
weird.
well,
Um,
I think that okay. I mean, I feel like it's. I was sort of joking. Like the last three papers I wrote, I modified quantum mechanics. So apparently, I'm kind of on the I have tenure now, and I'm headed that way. But all of the modifications were motivated by problems in quantum gravity. They weren't motivated by the weirdness of quantum mechanics. And I think we shouldn't reject theories because they're weird. We should
yeah,
reject them because there's some theoretical inconsistency in the theory.
for
And
sure.
so I'm happy to modify quantum mechanics for that reason. I'm just
But just to be clear, when you say modify quantum mechanics, you mean modify quantum mechanics in the presence of gravity. I mean, if you're talking
yes,
about quantum, yeah,
in the presence of gravity.
right. So
Yes.
ordinary quantum mechanics, you would keep, non-gravitational quantum mechanics is what it is.
If the observer is infinitely big, yes.
Okay.
But I would say if the observer has finite size, I would say it's modified even without gravity. But I would say you don't like somehow it's gravity that forces it on you that you need to confront that problem.
Okay. Okay. Fair enough. Quick thing before we end, there have been other approaches to resolving the black hole information paradox. Years ago, I shared an office with Samir Mather at Harvard. We were both postdocs back in the 1980s or whatever it would have been. I think it was the
Mm.
80s. Yeah, likely. And he, of course, has been developing these ideas of fuzzballs that sort of come out of string theory, a different view of black holes. What do you think? I mean, I think it's great that there are many ideas. I think that's a healthy thing for the field. But obviously, these other approaches haven't convinced you. Where do you think the field stands? I mean, do you put any weight on those ideas? And where do you say the dominant perspective of the community is right now?
Well, of course, that depends a bit who you ask.
For sure.
I mean, so yeah, I mean, certainly part of what Samir is saying, I think is correct, right? You have black holes have microstates. To really understand those microstates, you need string theory or something like it. Um, I think, yeah. So the parts of his story that involve concrete calculations in string theory, I'm happy with all of those. I think, I feel like there's something of a split in the field among the people who have really internalized how radical it is to say that space-time is emergent,
Yeah.
and people who still, in some sense, want to think of space-time as fundamental,
As what? As fundamental.
as
Yeah.
fundamental.
Yeah.
And, for me, ADS CFT settled that question. You've got the theory in front of you, and the fundamental description is the boundary description. And, the space-time in the bulk is only there in some approximation, only sometimes, and it's our job to figure out that approximation. Um, I think, yes, a lot of the arguments people make are still sort of back in Hawking's mindset, where you sort of take locality as a principle that just can't be conceded. Um,
Right.
yeah, and in particular, I think in Samir's sort of some of the less concrete things that he said, I would say he's taking that view, whether he admits it or not.
Yeah, I think it probably does. I think he's sort of moving the smallest steps away from, conventional ideas with the overlay of string theory. What does it require to resolve the issues? And he says, look, if black holes don't form, that would be a resolution to the issue, and it'd be a pretty straightforward one.
Well, yeah, so right, so that's the thing. So he'll certainly grant you that there's non-locality at the scale of the horizon.
Yeah.
Okay. And so now you have to ask him what it means. So now the next question is, what does it mean for the person who jumps into the black hole? Okay. And so if what he says, if what he says, this is not what he says, but if he said that that non-locality means you just go splat on the horizon and you don't experience the interior,
Right.
um,
Doesn't say that, but yeah.
then that's what we would call a firewall. And
Sure.
you can call it a fuzzball, or you can call it a firewall, you can call it whatever you want, but
Right.
splat. Okay. Um, but then you need to have a theory of where the firewall formed and why we're not running into them right now, and why during inflation, we did, when we look at the cosmic microwave background, right, we see across many horizons, and why that's okay, right? And so,
Yep. Sure. Sure.
okay. So then he doesn't want to, so indeed, he doesn't want to say that. He says you coast through and you don't feel anything bad until you hit the singularity. But now there's the question of, how does the information get out? And as we just discussed, locality at the horizon scale isn't good enough. You need locality over much longer scales in order for the information to get out. Um, yeah, I think that's just something that you have to make your peace with. And so, I wouldn't say that this is totally settled in the community. I mean, it's a pretty confusing question. There are always going to be people on various sides. I'll stand by what I said, which is, I think what we wrote is the first time where you have a model that has all three parts of Hawking's paradox. And you can see that 1, 2, and 3 star are self-consistent.
Right.
Now, I think that can't be argued with. It's mathematics. And now the question is that what's actually going on?
Right.
And that's much harder because, to be actually what's going on, you need the standard model, and you need, 3 + 1 dimensions, and you need a whole bunch of things that don't seem essential for Hawking's paradox, but certainly seem essential if you want to say it's what's actually going on in our world. And I want to emphasize something that I say to graduate students, but I guess I can say it here too. People sometimes claim, oh, we need more experiment, quantum gravity, it's all speculation, none of it's going to be testable, et cetera, et cetera. The number of quantum gravity theories that we have that fit all the data is zero,
Yeah.
zero, right? And so we're not limited by experiment, we're limited by theory. We have toy models that don't describe the real world, and we can try to use them to find a theory that does. But until we find one, we're limited by theory. And of course, it would still be nicer to have more experimental data, because we might not be smart enough to come up with the theory. And so then certainly experiment can help you come up with it. But you don't really need experiment until you have two theories that are consistent with the data. And then now you need more data.
Right,
Um,
for sure.